Okay, it's time to start the session. What does ADB lolcat do? A deep dive into ADB by Ravi Subramanian. Please give a warm welcome to Ravi.
Thank you all for attending. It's an honor for me to speak here. ここで話すことは名誉です。In this talk, we'll dive pretty deep into the internals of the ADB tool and the Android SDK, which you might be familiar with, mostly in the spirit of understanding more deeply the tools that we use on a daily basis. So really quickly, about me, I'm Ravi Subramanian, and I'm on the engineering team at an enterprise Android startup in Seattle in the United States. I have about 10 or more years of experience in the mobile space, worked on many mobile platforms, Windows Mobile, if you can remember that, Windows Phone, forks of Android, back from the Gingerbread days. I also recently published a course on building battery-conscious apps on LinkedIn Learning. So let's jump right in. What is ADB? As most of us know, it stands for the Android Debug Bridge. It has been around since the beginning of Android time. It's one of the oldest tools in the SDK, about 12 years or so. And at its most basic level, it helps you communicate and examine devices or emulators from a host, which is most likely your development machine. So let's jump right in and look at the components of ADB. At a high level, there are actually three pieces that make up ADB. There is the client, the server, and the daemon. The client and the server actually run on the host, whereas the daemon, as you can imagine, runs on the device or the emulator. So the client is what we're all used to when we type ADB lolcat, whereas the client doesn't actually directly talk to the daemon. The client actually talks to the server over TCP sockets. And then the server is the one that mediates communication between a client and the daemon. So that's kind of like the high-level overview. So if you want to look at some of the core concepts in the design, there are basically three core concepts. There are transports, which basically models the connection between the ADB daemon and the server. Then we have a protocol, which is the language that ADB, the daemon, uses to talk to the server. And finally, we have services, which are basically all of the functionality exposed by ADB. So let's take a quick look at transports. As you can imagine, it is basically purely responsible to abstract away any of the connectivity details between the host and the device or the emulator. And it also is responsible for handling simultaneous data transmission and multiplexing of multiple streams, actually, between the server and the daemon. So if you have multiple ADB commands in flight, they are actually multiplexed simultaneously, and the transport needs to support that. So there are actually a couple different types of transports. You're probably familiar with the USB transport. So this one is basically the transport that allows for communication between a host and a device when you plug it in over a USB cable, which is most likely the common scenario. There's also a TCP transport, which is interestingly referred to in the code as a local transport. But I think it's because it's used to talk to the emulators. So the server actually talks to emulators using TCP sockets, but locally on the same machine. So that's, and then the TCP transport is also used for Wi-Fi based connections of a server to the daemon. So there's a possibility of writing other transports. So in theory, you could proxy traffic between a server and a device that's connected to another remote machine. It's possible. There's actually a comment to this effect in a file that's 12 years old, but basically timeless. And I think there are some companies that have attempted this as well for emulators. Let's jump to the protocol. So this is essentially the language that's used to communicate between the host and a device. And it's also, it is a message-oriented protocol. Essentially, everything that's goes on between the computer and the device is in the form of messages. And as I mentioned previously, it's designed that way to allow for multiple streams to coexist over the transport. So if you think about how IP or TCP works, like you have headers that indicate what the destination and the port is, but they can all go over the same transport, so it's roughly the same concept. And one thing I found is it is actually a surprisingly simple and effective protocol. It's aged quite well, as we'll see shortly. There has only been one revision of this protocol since its creation. And basically, you can see here the version was 1 followed by 6 zeros. It's basically the first version, and that got bumped in December of 2017 to one later version. And we'll see shortly what that was about. So let's dive into the message format. This is essentially a C or C++ structure, and you can see there's a few different fields. So let's talk about some of the important ones. There's a command. The command is essentially the semantics of the message, like what does this message imply? What is it about? And the arguments are, they depend on the command, and they refine the command a little bit depending on what it is that the sender or the receiver needs to do. And then, well, there's the data length, which is obviously length of payload, and then there's data check. That thing has not been used since December 2017. Data check is supposed to hold the checksum of the data that's going into every single packet or a message that's being sent back and forth. And it turns out there was a change that went in where they just stashed the value 0 into it now because they found out, according to the comments in the commit, it was pretty interesting. When they were computing it, or rather when they stopped computing it, it improved the throughput on USB 2 by 40%. And it wasn't actually adding much value, so they decided to take it out, which I'm good about. So these are the message types. I won't go through all of them, but we'll actually revisit them later. What I wanted to show is that this is basically it. There are 6 types of messages in the protocol. So it's a pretty simple, as I said, easy to understand protocol. Now let's talk about services. These are the supported capabilities by ADB. So what do I mean by that? There's basically 2 types, actually. There are host-side services. What this means is when you type, say, as an example, ADB devices, if that's something you've ever tried before, that will be completely fulfilled on the host side itself. There is no need to talk to a device to figure out what actually, or to actually perform the operation. As opposed to device-side services, which is like lolcat or shell and all of our other friends, those are things that need to be fulfilled on the device. So there's that little distinction there, like host services and device services. Again, there's references to device services as local services. And that's, I think, because they could run on the emulator, which actually runs on the same local machine as your host. And that's, I think, the reference there. And as you can imagine, this list of services will grow over time. Fun fact, the most recent service that I could find that was added was ADB Reverse. It was sometime in 2013. That was, as you can imagine, more things can be added as and when needed. So as we start diving deeper into each of these and to understand what actually happens under the covers, it would be useful to actually focus in on what each of the components do. So let's take a quick peek at what the ADB client does when it actually kicks up. So when you actually type in ADB lolcat, the first thing it actually does is does some trace initialization. So there's this little trick where if you are really interested in what ADB does under the covers, you can set the ADB trace environment variable to a variety of values. So you could just say all, and it just spews out a bunch of interesting tracing information. So it needs some setup for that, so that happens first. This is the interesting part, then the command line parsing, as you can imagine. So the first thing are options. So in my example there, it just says ADB lolcat, but you could say ADB -T to pick a particular transport, or -L for something else, I forget. That parsing happens first. After that, it actually attempts to talk to the server on the same machine. If the server doesn't exist, it actually launches the server. You may have seen this little thing printed out saying launching server. And this is, if you're interested, the actual command that gets executed. So this is a fork exec paradigm, basically. So it parses, after it launches the server by forking it, as you can see, ADB starts itself with these parameters. And then when that second ADB parses its parameters and says, and encounters fork server, it goes, oh, I should run as the server. So it actually execs itself as the server. And then the client processes the arguments in lolcat in this case. There's also this little trick that you may or may not know. You can say wait dash for dash and then a transported state. So the quick example is wait for device. So you can say ADB wait for device lolcat, and that'll actually wait for a device to be connected before it actually attempts to run the next command. This is useful for like automated testing, for example. And then it processes the command. In this case, in this example, it's lolcat. It does a server version handshake, and then it formats and sends that command over to the server to actually do its thing. As you can imagine, in the case of lolcat, then it enters into a loop, which we'll dive into a little bit later, where it's constantly receiving information through the server and then just printing it to the screen. So some of you might be wondering about why my talk says lolcat. Lolcats were fashionable maybe, I don't know, 5 years ago. But plus, I mean, the documentation is pretty clear. It says lolcat. But, I mean, it was not a typo. It's actually, if you look at platform system core, the command line.cpp, they actually support that command. So you can type in adb lolcat, or you can type in adb lolcat. And a little trick, you can type in adb longcat, which is something I learned, which just ends up printing out even more information. So yeah, I don't know the history behind that, but I thought that was really interesting. So now you can believe me. All right, let's dive into the server startup now. Whoops. Well, okay, you know what I'm talking about. So the server, as I mentioned previously, is started by the client. First thing it does, it actually sets up a detection mechanism for devices that come online. So if you recall, the server is kind of like the mediator between the client and the daemon. So the server needs to listen for devices that come online, like, for example, when you plug in. So it actually sets up some stuff to detect devices like that. It sets up MDNS, which is like Apple's Bonjour support. So actually the server can discover devices that are named that way over Bonjour. And then it does a USB initialization. So the detection mechanism up top there is designed to detect if a device gets plugged in after the fact. But if a device is already plugged in when the server starts up, it needs to run that once manually. So that's what happens here. Then this is kind of like the important part. If you remember, I said the ADB client talks to the ADB server using sockets, TCP sockets. So it actually installs a TCP socket listener for every single command. So every single command comes in on a new socket. ADB lolcat, ADB shell, whatever it is that you type in. Each one is a new socket. So there's that. Then it does one more thing. So there's this dance that needs to happen between the server and the daemon, because a device needs to authenticate a host and allow it to talk to it. So the server side of the story is it actually loads up a private key from that location there in preparation for a device querying it during the authentication phase, which we'll talk about in a little bit. And then finally, there's a run event loop, which is a classic Unix select loop. So it has a bunch of file descriptors open and it's just waiting for events to happen. And that's your server right there. And now we'll take a quick look at what daemon does. So the daemon's actually started by the Linux init. As if any one of you is familiar with embedded programming, like init is like the first thing that runs. And so it's always started at the beginning when the device boots up. First step again is transport registration. Now remember, this is the device side of the equation. So here what it does is it registers to be detected to be plugged into the host. So it's kind of the inverse thing. Then it creates, this is interesting, it creates a control socket. This is like a named Unix socket. It's called dev socket adb, and it uses it for the authentication workflow, which we'll talk about in a little bit. It also then drops privileges. So if it's running in secure mode, which is the default on most devices, it will stop listening on the TCP port that it actually listens to by default, and then it also will not run as root. It actually reduces itself to the shell user. And this is related to why you might see, if you try to do ADB root, it'll say ADB does not run as root on production builds. That's kind of related to that. And then it also sets up the listening ports and MDNS listeners on the daemon side. It actually allows for connections, socket-based connections as well. And finally, it initializes JDWP, which is how debugging works on Android devices. So JDWP stands for Java Debug Wire Protocol. This is the protocol that any Java app that wants to be debugged, so the JVM that it runs on, talks that protocol to the debugger. So it's basically the same protocol used on the VMs on the Android devices as well. So every app that is debuggable actually sets up a socket to send JDWP commands over. So that actually happens through the ADB daemon. And finally, it runs an event loop just like the other server. So that's like a quick, in a nutshell, overview of the startup of what these three things do. Let's get into a slightly more interesting part. So what actually happens now when you type in ADB lolcat? So it makes sense to look at a couple of protocol traces. There's actually two. There's host authentication, which happens before any ADB command can run. And then there's, of course, the stuff that happens when you run a command. So let's look at both of them. So let's first look at host authentication. This is what happens, as I just mentioned, when you, let's say you take your device and you plug it into a dev machine. So what happens there? Let's take a look. So you have your server and you have your daemon. So let's pretend that a device just got attached over USB. So that's the first step. What happens is the server sends over the transport a connect packet. This A, CNX, and A connection is kind of like the internal, the enumeration value in the code. So it sends an A connect packet over to the daemon and says, hey, I want to connect. The daemon goes, I don't know if you can read that. It basically says it handles the new connection, and as part of that, it runs this method called send auth request. So the first time you are actually trying to connect a device to a host, the daemon will say, who are you? So it sends an auth packet. And it sends that with an argument of ADB auth token and sends a token. This token is just a random number. And it expects it to be signed by a private key. So it's expected to be signed by actually a pre-existing private key on the server side. And then expects the server to send back an auth message, but with an argument saying ADB auth signature. So the data is basically the signature of the token that it just received. The daemon now will invoke the auth verify. And now note that with good old public key, private key style of signature verification, the server actually holds the private key. The daemon is expected to hold the public key, and they kind of the daemon performs the check with a known public key. And what's supposed to happen now is, if that verification fails, let's say, if the private key that was used to sign doesn't match the public key that the daemon is aware of, this now has to happen a few different times. So how does this work? So basically, on the server side, there are actually a few different places where the server that's running on your development machine, the ADB server, actually looks at a few different places for private keys. It looks at the .android/ADB key, and it also looks in any place specified by that environment variable, ADB vendor keys. And then it basically goes through them one by one and tries to sign as long as it hasn't succeeded yet. It keeps rolling through those private keys. Same thing on the daemon side, actually looks at these two different directories for acceptable public keys to verify against. And each time it gets back an auth request, it tries to check against that. So presumably one of those works, and it says yay, and so sends back a connection packet and goes, here you go, you're good to go now. And so on the server side, now it just marks that device and transport as verified. So this is kind of like your typical flow of auth. Now, what happens if none of those public keys actually work? So you might be interested to know that, for example, the key pair that's inside .android / the ADB key, that's actually generated if it's not found. So if that key just got generated on your dev box, there's no way it's going to be found on the device. So that's essentially the first time when you try to connect a device to a dev box. Well, so it sends, if it runs out of private keys to sign it with, it says, I give up, here's a public key. So here's my public key, and it actually sends the public key over to the daemon. So well, what happens there? Let's actually take a peek in that. So as I mentioned previously, this is the daemon now, and on the right side I'm showing you the USB manager, which is a framework component in Android. So there's this control socket that got created earlier, as I mentioned. Now the USB manager is actually listening on the other end of the socket, and it's holding on to that other side. So now when that public key gets sent over to the daemon from the server goes, okay, the dev box sent me a public key. Let's call ADB auth confirm key. So let's confirm this key. So what it does is literally writes the string PK followed by the public key signature into that socket. That actually gets read by the USB manager at the other end. So what it does there is actually does a user prompt. So if you can look here in the code, this is inside the USB debugging manager. Notice on line 138 towards the middle, it's literally checking for the two characters P and K, and then says, oh, all right, let's pop up an ADP confirmation box, which is that famous screen that you guys probably know. So now let's say you're a good developer, so you say, okay, what happens then? Well, that literally the two letters O and K get written back into that socket. And then they make it back over to the daemon. And the daemon, this is inside auth.cpp on the daemon side, literally checks the two letters O and K and says, all right, it sounds like the user wants to hold on to this public key. So let's write it to disk and save it. So basically it says auth verified at that point. So coming back to here, what happens there? If once the user says OK and it gets verified at the daemon side, it sends back a connect packet, and then now the device is authenticated. I'm sorry, the host is authenticated against to the device, and now that transport is good to go. So this is basically the flow of this is the auth flow that happens every time you connect a new device to a developer box. So having set the stage there, now would be a good time to look at the protocol trace for what actually happens when you type in ADB lolcat. So once again, we have the client and the daemon. So when you type in the command, remember that if the server is actually not found, it gets forked and created at that time. So let's say the ADB server gets created when you actually, for the first time. What happens is that, so now the socket is open. This is a local TCP socket between the client and the server on the same machine, on your developer machine. It actually sends the string host : version. This is kind of like a version handshake, basically. And the host : just means this is a host side service. I don't intend for you to send this to the device. And it basically says, hey, what's your version? It responds with an OK and says it's 40, and 40 just happens to be the most recent version of ADB. This is important because, as I said before, the client forks the server and actually creates that process. There's a small chance that you upgraded your SDK tools in the middle. There's still an ADB running in the background, and ADB's version got bumped. So then there will be a mismatch. So let's just pretend 41 got released. So then when ADB client tries to talk to the server, there's a version mismatch. It actually kills the server and restarts it. But then it says, with ADB lolcat, you just said, give me the logs. You didn't say which device. So it just says, use any transport. So it sends host::transport any to the ADB server. Now, the ADB server basically picks the one device that you implied. Now, if for any reason you have two devices or more connected to your host, that's actually ambiguous. So it'll actually won't know what to do, and it'll be an error in that case. But let's pretend there's only one device connected, so you get back an OK from the server back to the client. Now, at the same time, the server actually sends the A open to the ADB daemon. Now, the payload of that A open packet is the literal string. I'm sorry if you cannot read that. It says shell::export Android log tags equals empty string semicolon exec logcat. It's literally a little shell string. It's a shell script. If you had log tags set to a particular filter value, that gets included in there too. So when that gets sent over, now the daemon receives it and actually uses that shell colon to map to the corresponding service, which in this case is the shell service. So interesting fact, the logcat service is actually just handled by the shell service. So ADB logcat is essentially the same as ADB shell logcat. So it's just a little something. If you're wondering, there's a logcat binary that's what gets run on the device side. So it uses a fork and exec paradigm to start the shell, and then the shell essentially execs itself and now becomes the logcat process. So there is a logcat binary running on every Android phone, and that thing will start reading from the log buffers. All right. So now you start seeing logcat messages sent over from this process over a file descriptor to the daemon. So as you can imagine, now it's like a fire hose coming through. So for every one of those messages, it creates an A write packet and pops it over to the ADB server. And then the ADB server receives that over the transport, rips out the data, and then puts it in a little queue. And so this happens very quickly. And then that queue of messages is being pumped on a separate thread. So it just writes the message to the queue and then immediately says A-OK back to the daemon. So this is kind of like a flow control mechanism, essentially. And now the server then just takes every one of those messages and sends them over the socket, the local socket, back to the client. Now, as you can imagine, this will keep on going as long as log messages keep on coming. So, one of the things that could happen is you figured out what's going on and you're sitting in front of your computer and you go, Control-C, I'm done with the logs. Well, what happens then? The socket actually closes. The socket between your ADB client and the server on your local machine now dies. That actually gets detected by the ADB server. And the ADB server sends a close to the daemon. And that causes it to basically send a kill command to the logcat process. And so basically, logcat dies, and you're done. So I'm just going to leave it there for a second for you to digest that. Okay, so on to the next slide. So some quick stats, because I still have a minute, in case you're curious. All these three components, the client, server, and the daemon, are all built from the same source code. That's the link to the mirror of the Android source for the system platform system core project. The client and the server share the same binary, as I just explained, and the client starts the server. The device-side daemon also is actually built from the same code. It just happens to be built for ARM or x86 to run on the emulator. And in case you're curious, just at a quick line count of the ADB source, it's a lovely 20,000 lines of C++ code, evolved over the last 12 years, and a little bit of Python for testing and stuff. So, but I found that it was pretty robust, and it has aged quite well. So that's all I have. Arigato.